have touched on and worked with IP addresses in many throughout these modules and courses. And so in this, I want to go over some basics with you regarding IPv4.
Number one, an IPv4 address is 32 bits in length. And instead of writing it out in a bunch of ones and zeros, etc., 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 what we do as humans, we represent them as 4 decimal numbers, like 192, 168, 1, 102. And then we put periods between those numbers just to separate where the numbers start and stop. So we represent it as decimal, and behind the scenes it's binary. Now, a part of this IP address that server 2 has right here represents the actual network ID, and a part of that IP address represents the actual host portion. And the way we determine that is using the mask. And what the mask does is simple. It simply identifies where the network portion stops and where the host portion starts. For example, in our case right here, it's right here. And the way it does that, it represents how many bits are being used by the network. So /24 means that the first 24 bits are the network, then the remaining 8 bits over here on the right represent the host addressing on that network. Now, for the purposes of unicast routing, we have 3 classes of addresses, class A, B, and C. And it's really easy to identify a class A from a class B from a class C. All we do is simply look at the very first number, the first octet before that first period. And for a class A, that very first octet is going to be between 1 and 126. There's also a 127, which is also a class A address, but it's reserved for loopback purposes. So as far as routable class A addresses, the first octet would be between 1 and 126. For a class B address, it's between 128 and 191. And for a class C, it's 192 through 223. And the question may come up, well, Keith, why do we even care about class A, B, or C? And today, we pretty much don't, because we use whatever masks we need to. However, there are some default masks, and here they are. A default mask for a class A address is 8 bits, meaning the first 8 bits are the network, and the remaining 3 octets, or the remaining 24 bits, are used for host addressing. With the class B address, the default mask is 16, and with the class C address, the default mask is 24. And we don't have to use those conventions, but those are the defaults. Another thing that's important to be aware of is that there are some private address space based on an RFC. It's RFC, that's a request for comments number 1918. And in RFC 1918, it allocates some address space from each of the classes that can be used inside companies. And when the companies use those addresses inside, they don't have to tell anybody about it. They don't have to register or request addresses. They can just go ahead and use them. And the RFC 1918 addresses any IP address that begins with 10. And I'm going to say 10 anything. So we have an example of one right here. We're using a 10.0.0 network with this last 24-bit mask. And that's an example of an RFC private address in the class A range. And in RFC 1918, for a class B address, there's a 172.16 through 31 dot anything. And for class C, there's a 192.168 dot anything. And that's the RFC 1918 private address space in the class C range. Now, one thing about these RFC 1918 addresses is that they're not routable over the internet. So service providers are going to knock those off right at the edges. So if we're using a private address like this one right here, 192.168.1, which is an example of the RFC 1918 private address space, what we'd have to do is do network address translation before those packets are sent out to the public internet. Now, one of the challenges that comes up with IPv4 is the concept of subnets. Now, the idea of subnets isn't too tricky. Sticking one network, for example, the 10 network, with the default mask of /8, that's again from the RFC 1918 private address space, and then carving it up into multiple subnetworks. And to understand what's really going on there, it takes a little bit of time with binary to look at what's going on behind the scenes. So regarding subnets and how they're created and how they work, I've got a few videos that will walk you through some of the basics of binary and how to do custom subnetting. Another challenge that comes up is routing and reverse engineering with IPv4. Now, from a routing perspective, when a Windows server gets a packet, it's going to forward it based on its routing table. And if routing is enabled, it's also willing to forward other devices' traffic through it. But in either case, it's going to refer to its routing table when it's making a routing decision. And so as we look at this routing table, the rule is we're looking for the longest match in the routing table. That's the route we're going to use. So as I look at the entries here, I don't see anything that starts with 23. And as a result, it's going to go to the default route. I call it the Obi-Wan Kenobi route. Help us, Obi-Wan. You're our only hope. And so in this example, I'll use the default gateway at 192.168.1.1 to forward that packet. Another challenge that comes up is the need to be able to do reverse engineering. For example, let's say we saw a computer and we looked at its IP address, and let's say the IP address was 23.17.204.98, and it had a mask of 19, meaning the first 19 bits of the IPv4 address are representing the network, and the rest is representing the host address. A good question is, what exactly is the network, the subnet, that this host is connected to? And the ability to take a host address like this one with a mask and reverse engineer the network ID, the subnet ID, also requires, my friend, a pretty good understanding of binary and subnetting, and have no fear. That's what the next several videos is going to walk us through together.
I'd like you to imagine that you and I have walked into a showroom floor. It could be cars or boats or what have you. And on one of the items that we're looking at, it has a price tag and it says this, 45,239. And I want to ask you, how much is that? I'm talking about the actual number itself. Now you might be saying, well, Keith, this is really obvious. It's 45,239. That's the number. And how did you get that so quickly? And the reality is because we've been using base 10 numbering system for all of our lives. It goes something like this. We have several positions here. For example, the 9 is in the 1's position, and the 3 is in the 10's position, and the 2 is in the 100's position. The 5 right here is in the 1,000's position, and the 4 is in the 10,000's position. And all we're doing, because we use a base 10 numbering system, is the first number is always a 1, and then the next position is times 10 and times 10 and times 10 and times 10. In fact, we could go all the way down, just continuing to multiply that placeholder by 10 by 10 by 10. And really, it was 4 10,000s, it was 5 1,000s, it was 2 100s, it was 3 10s, and 9 1s. But this is so second nature to us, we didn't have to break it out like that. In fact, when we count, for example, our numbers go through 0 through 9. So we have 10 distinct numbers to play with, 0 through 9. And when we count, we do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And what do we do next? We simply carry the 1 into the next position, and we put a 0 here. So 1, 0 in decimal represents 1 10 and no 1s for a total of 10. And then we go to 11 and then 12. And then if we get all the way to, for example, 999 by continuing counting, and we need to go one more, we carry the 1 again. And we have 1,000. Now you might be asking, okay, Keith, I totally get this. This is base 10, the numbering system most humans on the planet have been using our entire lifetimes. So what has that got to do with this thing called binary? Well, binary is simply a different type of numbering system. Instead of using base 10, binary uses base 2. So with base 10, we had numbers of 0 through 9, which are 10 individual separate numbers. And with base 2, we have 0 through 1. With a base 2 numbering system, the first position over here on the right is a value of 1. And then as we move left, this next position is simply this first number times the base. So in the case of binary, it's base 2. This would be 1 times 2. And I'll put that right here, and that'd be 2. And this next position over here, this next placeholder is going to be this number times 2. So that would be 4. And then as we go left, it would be this number times 2, which would be 8. And then times 2, 16. And times 2, 32. And times 2 again, which would be 64. And times 2 again, which would be 128. So with a base 10 numbering system, it went 1, and then times 10, times 10, times 10, etc. With base 2, we start with 1, and it's times 2, times 2, times 2, times 2, etc. It's also important to note that although we could go a really long way left here, we really only need to worry about 8 positions at a time when we're dealing with things like IP version 4. I want you to write out these value positions for binary. And again, the way to do it is you start on the right with a number 1, and then you simply take that number and multiply it by the base as you go left. So please take a moment and make sure that you can write this out on demand. So let's take a look at an example of how a binary number works. Now in binary, there's only 2 numbers that we get to play with, and they are a 0 and a 1. See, in decimal, we had 0 through 9, 10 different positions. In binary, we have 2. We have 0 and 1. It's sort of like a light switch. Either it's off or on. That's our only 2 choices. So if we had a binary number like this, that's 1, 0, 0, 0, 0, 1, 1, 0, holy schnikers, what exactly is the value of that number to us as humans? And the way to figure that out would be saying, okay, well, we have a 1 in the 128th position, so that's 128, plus 0, because we have no 64s, plus 0, no 32s, plus, okay, how many 16s are we going to add to this equation? If you're saying, well, Keith, it's like a light switch, right? It's either on or off. Because this is a 0, it's off, which means we don't have any 16s, so we're going to say 0 there, plus 0. And here we go. In this third position, we have a 1 on in the position that's worth 4. So we'd add 4 there, and how about the 2? The answer is, yep, we have one of those, so we'll add a 2 as well, and then 0. And then it's simply a game of adding. All we're going to do, if we want to find out the actual value of this binary number, all we simply do is add these up. So it's 128 plus 4 plus 2, and that's it. So 8 plus 4 is 12, plus 2 more is 14. We'll carry our decimal 1 right there. That's a 4. 2 plus 1 is 3, and then we have a 1. And so the actual value of this binary number, 100000110, is 134. I remember seeing The Wizard of Oz, and near the end, they pull back the curtain to reveal who really is acting as the wizard. And that's what I'd like to do right now with IP version 4. Even though IP version 4, it's represented as dotted decimal. Here we have 4 numbers right here, and they're separated by 3 periods. What's really happening is that's just for us humans as a convenience. What's really going on behind the scenes is that each one of these numbers represents 1 byte of data, 8 bits, which go into 1 byte of data. So each of these numbers, 130, 16, 33, and 17, sometimes these numbers are referred to as an octet. And an octet is nothing more than 8 bits that are all represented together in the same grouping. So whether you want to call this first number the first number, or the first byte, or the first octet, all of those mean the same thing. Now the great news for you and I is that in converting, if we needed to convert binary to decimal or decimal to binary, it's really straightforward because in either method we're going to first write out this table. We have a decimal number that we're going to convert to binary. So we're going to do that one first. And it's really just a game. And I call it the does it fit game. And here's how we play it. We take a number. So we're going to first start with 130. And we're going to write it out. And all we need to do is take this very first number on the far left, 128, and ask ourselves the question, does it fit? Does 128 fit into 130? Yes or no? It's a binary question. If the answer is yes, we're going to put a bit on in that position. And we're also going to subtract that value of 128 from the number we're trying to convert. So the remainder of this is 2. 130 minus 128 is 2. So we take that remainder and we play the game again. Does 64 go into 2? No. Well, it might a fraction of the time, but we're looking for, does that number go in an entire time at least once? And if the answer is no, it doesn't, we put a 0 there. How about 32? Does it go into 2? No, it doesn't, so that gets a 0. Does 16 go in? No, it doesn't, that gets a 0. 8, does it go into 2? Nope. How about 4? Nope. And then we get down to 2. Does 2 go into 2? And the answer is yes, it does. It goes in exactly 1 time. So we'll subtract 2 from it, and we are down to 0. So the question is, does 1 go into 0? And the answer is it does not. And so we're going to put a 0 there as well. It's sort of like accounting. If you love accounting with debits and credits, trying to get them to equalize, that's all we're doing here, is we're trying to whittle this number down to 0. So this number right here, 100,00010, is 130 in decimal. So let's do one more together, and let's go ahead and do 16. The game is, we want to convert 16 into binary. We're going to play the does it fit game, so we're going to write out on our paper 16, the number we're after, and ask ourselves the question, does 128 go in? The answer is no, negative. Does 64 go into 16? No, negative. Does 32 go into 16? It does not. Does 16 go into 16? The lights go off. Yes, it does fit. So we take that number that we just put in, we subtract that from our number, we take the remainder, and we play the rest of the game. You can't stop playing until you've given all 8 bits in that octet or that byte. So 8 doesn't go into 0, nor does 4, nor does 2, nor does 1. This is our binary number that represents 16. It is 0001 0000. So we're going to input, when we configure routers and devices with IP addresses, we're actually going to put in the value of 16 for that second octet. But what the computer knows, or the router knows, is that this is the binary value of that second octet. I'd like you to take this number 33, and your mission, which I hope you accept, is to convert 33 into the 8-bit binary number that 33 is representing. What I would encourage you to do is start by writing out this table and then simply writing out 33 and playing the game called Does It Fit? So does 128 go in, does 64 go in, etc., etc. Every time it does go in, you put a 1 and you subtract that value from your number and play the game again, continuing on with the remainder. So go ahead and pause me right now, work out the binary equivalent of the decimal 33, and when you come back, we'll validate what that answer is in binary. So the game goes like this. 33 is right here. We say, does 128 go into 33? The answer is no. 64 doesn't go in. 32 does. So we're going to put a 1 there. We'll say minus 32, and our remainder is 1. 16 doesn't go, nor does 8, nor does 4, nor does 2, but 1 goes in cleanly one time, and our accountant is happy because we've had a 0 balance at the end, which is how it should be. So the decimal number of 33 is representing our binary number of 001, 00001. If that's the answer that you got, absolutely great job. What if we needed to convert a binary number that we're given in binary to decimal? Let's say we're given a binary number of 101001111. How do we convert that to decimal, the decimal equivalent? Well, the answer is we're going to take everywhere there's a 1, we're going to take that value from the placeholder it's in and simply add them up. So we're going to add up 128 plus 32 more plus 4 plus 2 plus 1. So we can do that longhand. 128 plus 32 plus 4 plus 2 plus 1. 8 plus 2 is 10, plus 4 more is 14, plus 2 more is 16, plus 1 more is 17. There's our 1, there's our 7. Then we have in this column 3 plus 2 plus 1 is 6. And in the hundreds position we have a 1. So that value of this binary number right here is 167. And I put 167 equals 167. I guess that's a little bit redundant. So in converting from binary to decimal, we simply look for the ones and then add up the values of those positions for our equivalent total value. So now it's time for your exercise in converting binary to decimal. And what I'd like you to convert is this number right here into decimal. So go ahead and pause me. When you're done, go ahead and resume, and we'll confirm our answer. All right, welcome back. Let's see how we did. So for this answer, which we'll call option number A here, we have 64 plus 32 more plus 16 more plus 4 plus 2, and that's it. So if we add all of those up, there's 4, 5, 6, 6 more is 12, plus 4 is 16, plus 2 more is 18. We'll carry the 1. There's an 8. So for the tens position, we have 6 plus 1 more is 7, plus 3 more is 10, plus 1 more is 11. That would be 118. And if that's what you came up with, congratulations. You have the ability to convert from binary into decimal. Now let me give you a couple more that I'd like you to practice with as well. Let's take this one right here. Well, 000000000. I want you to do that one if you would, as well as this one, 1111111, and one more. Let's have you go ahead and do 11110000. And we'll call those A, B, and C. And what I'd like you to do is write out on paper what the decimal equivalent of A, B, and C is. And if you're saying, Keith, I think I've got the A, it's 0, you'd be absolutely right. It might take you a little bit longer for B and C, so go ahead and pause me while you do all three of those, write out your answers, and then click on resume, and we'll compare notes. Okay, welcome back. So let's take this first one, option A first. And option A is 0 plus 0 plus 0 plus 0 plus 0 plus 0. Okay, so A equals 0. Now this next one, we have some more adding to do. So we have 128, and here's what I'd recommend. Don't just do it in your mind. If you're new to this, do it as we have in this video by writing out like 128 plus 64 plus 32, which is what this is all about. So for answer B, it'd be 128 plus 64 more, which is 192, plus 32 more, which is 224, plus 16 more, which is 240, plus 8 more, which is 248, plus 4 more, which is 252, plus 2 more, which is 254, plus 1 more is 255. So B equals 255. And you might say, well, Keith, you did that in your mind. You didn't even write that out. And that's because this is one of those values that you're going to see a lot of 255. And it's just because of raw practice with these numbers that I can do that in my head. Otherwise, I'd be writing it out. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255. And for answer C, we have 128 plus 64 plus 32 plus 16. And if we add all that up, the long way, the short way, use a calculator, what have you, it's going to end up to be 240. If those are the three values that you got before we compared notes, my hat's off. If you didn't get these three numbers, I would ask you to go back manually, like we did right here and here, and add them up once again, just to confirm that you're doing the conversion from binary into decimal correctly. Also, the valid range, if you will, for any octet, any number in IP version 4, is going to be between 0 and 255. It can't be any lower than 0, because then we're going into negative numbers, and it can't be any higher than 255. Because in an octet, if every single binary number is on, the maximum it can ever get to is 255. But I also, just with a little caution, also want to point out that 0 through 255 is actually 256 different numbers, because 0 indeed is a value. But the numerical high number you're ever going to see is going to be 255. I'd like you to imagine that a friend walks up to you and in casual conversation they ask you, "Can you tell me," says your friend, "about a mask, exactly what it does?" Now if you're saying, ooh, Keith, I know, it absolutely identifies out of an IP version 4 address, it identifies which portion of that IP address is the network, and everything else beyond that is the actual host addresses. So here, my friend, are the details behind how the mask identifies which portion of an IP address is the network. So I ran ipconfig on my Windows machine, and this is what it gave me. It said my IP address is 192.168.1.15. Fantastic. So I broke that into binary just for display purposes. And the first number of 192, I put in red in binary here, 168 right here in blue, the 1 in green, and the 15. So there's the decimal notation that we normally use and the binary equivalent of each one of those. Now what I'd like to do is talk about the mask. There is also a 32-bit mask associated with each IP version 4 address. So in the output of ipconfig up here, it says that my mask, and that also brings me to a point of nicknames. For example, sometimes it's referred to as the mask, sometimes it's referred to as the network mask, sometimes it's referred to as the subnet mask, but any way you slice it, when we're talking about IP version 4, it's referring to this device that identifies which portion, going from left to right, which portion of that IP address is the network and which remaining portion is available for host addressing. So this is how it does it. That 32-bit mask is also represented in dotted decimal. So I have the mask right here. There's 255.255.255.0. So that's the mask literally off of the computer that I'm using. For display purposes, I converted the mask octets into binary. So there's the first 255 and the second 255, the third 255, and of course this last octet of all zeros represents that decimal 0 right there. So here's the magic. The computer lines up all the bits of the actual IP address with those same bits in the mask as shown here. And so here's what the mask does. We simply follow the bits that are on. The bits that are on in the mask is representing which portion of the IP address is the network. So if we simply follow the mask and the bits that are on and then stop when they stop, which in this case happens to be right here, that, my friends, is the dividing line. Everything to the left is the network, and everything to the right is the actual host portion. So in this case, we could say that my computer is on network 192.168.1, the first 3 octets, and that my host address is .15 on that network. The way it actually determines this is by doing some multiplication. It multiplies the bit in the mask against the corresponding bit in the IP address. And if we did that, for example, 1 times 1 equals 1, and 1 times 1 equals 1, 1 times 0 equals 0, effectively, we're going to have the same exact number that we have up here down below. And the very last octet, what it's going to be if you multiply all those by 0, they're all going to be 0 no matter what. So if we converted this back into decimal, it would be 192.168.1.0. And that's how we represent networks inside of IP version 4. And more specifically, we could put a slash here and say 24, which literally means that the first 24 bits, 8 bits here, and 8 bits here, and 8 bits here, those first consecutive 24 bits going from left to right represent the network, and the last 8 bits are available for host addresses, or like house addresses, on those streets. I've got a little exercise I'd like you to do with me, and that is this. Let's pretend that this mask isn't this one right here, so we're going to replace that for a moment, and let's say that the mask instead is 255.255.0.0. So the mask in this octet would all be zeros, just like that. And here's my question for you. Now that we have this mask, what is the actual network address, if this is our mask, and how many bits of the IP address are being used for network, and how many bits are now available for host addressing on that network? So take a moment right now, go ahead and pause me, determine what you think the correct answer is for the actual network address, and then we'll compare notes. Awesome. Thank you for taking a moment to do that. So here's how I would look at this. I'd say, well, we're going to follow the bits in the mask until they stop, and then you can, draw a line. And everything to the left of that is the network, and everything to the right are the host addresses. So we could say that with this mask, the network is 192.168, and then anything beyond the mask, when we're identifying the network, we just zero out. So this is the 192.168.0.0 network /16. It's a 16-bit network, and we have another 16 bits available for host addresses on that network. Let's do one more exercise. Let's go ahead and change the mask, and we're going to make it 255.0.0.0 for our new mask. So this is going to be a 0 and a 0, and we're going to have all these zeroed out here as well. So now if this is what our computer showed us, now my question is, what is the actual network address that this computer is on? How many bits is it? How long is it? And how many host bits are available? So go ahead and pause, make your decisions, and then let's compare notes after you resume. Thanks for taking a moment to do that. So here's one way we can approach this. We simply look at the mask first. That's the very first clue. And we're going to say, okay, this mask says that the first 8 bits are being used for the network. And if all the rest of the bits are zeros, that's the dividing line. And the cool thing is about a mask, it won't jump. This network mask or subnet mask doesn't jump. They are going to be contiguous bits moving from left to right. So a mask will never say 110111. It's going to be contiguous. So because the dividing line is right here, our very first octet is the network. Everything after that is zeroed out from the network address perspective. And that's 8 because it's the first 8 bits representing the network. And now we have the remaining 24 bits of that IP address, which are now representing host addresses on network 192. So let's do one more example to help reinforce the concept. Let's say we have a Macintosh or a Linux or a Windows box sitting on a network, and it's a happy computer. You want to know why it's so happy? Because it's got an IP address. It's got the IP address of 10.25.3.99. That's its IP address. And guess what it also has? It also has a mask. That mask in decimal is 255.255.0.0. 10.25.3.99.0.0. And what I would love for you to do right now is tell me what is the actual network that this computer is sitting on, what is the host address for this computer, and what is the number of bits that are currently being used by that network for network addressing, and how many bits are left over for host addressing on that network. So take a moment, go ahead and pause me right now, take as much time as you need, and once you've calculated what the actual network address is that this computer is sitting on, go ahead and resume me, and then we'll compare notes. Awesome. Welcome back. So in this example of 10.25.3.99, the very first thing we're going to look at isn't the IP address at all, it's the mask. Because the mask is controlling which portion of that IP address is the network and which portion is available for host addresses. And the mask is saying, I'm consuming, I'll use green for this, I'm consuming the first octet for network. So we know that the 10 is part of the network address that the computer is sitting on. We also know based on the mask that the second octet is also consumed and being allocated for the purpose of network addressing, and that's it. The third and fourth octet, the mask isn't taking anything, so we can draw our dividing line right there. This computer is sitting on network 10.25, and then we simply zero out the bits that host addresses are going to have, 0.0 as we describe the network, and that is a total of 8 bits here and 8 bits here, a total of 16 bits being used for the network address. Now that also implies that we have 16 bits left over that are not being used for the network address portion that we can then use for individual host assignments on that network. So this computer with the IP address of 10.25.3.99, the first two numbers are the actual network right here, and the last two numbers of 3.99 represent the actual host portion, or this guy's unique identifier on that network regarding IP addressing. And as we mentioned, there's 16 bits being used for the network, and there's also 16 bits available for host addressing. I'd like you to imagine that you and I have shown up for work one day, and our boss meets us with a big smile on their face and says, "Can you help me with a small project I'm working on?" And we say, "Sure, what do you need?" And our boss shows us this topology right here, and they ask us, "Can you put this together? We have a pilot program we're doing, and I want to just test some things. Can you make that all happen?" And we say, "Sure." We've got some extra gear, so we round up some routers, and we connect them with switches, and then we go ahead and do the addressing. So maybe over here on this network that is common to R3, R1, and R2, we use the network 192.168.1.0/24. Now if we analyze that, that means that the first 24 bits of this number, which is the first 3 octets, are the network, and this last octet is available for host addressing. And then for this network right here between R2 and R4, maybe we use the 192.168.2.0/24. And for the network between R4, R5, and R6 right here, maybe we use the network 192.168.3.0/24. Now, once we've implemented these IP addresses, we go back to our boss all proud and say, "Hey, we're all done. Take a look." And he looks at it on paper and says, "Oh, I forgot to tell you something." And we say, "Oh, what's that?" And the boss says, "This kind of needs to fit into our existing network. And if you could," says the boss, "I need this entire topology to fit in this space of 192.168.5.0/24. I want to use that network to support this entire topology." Now at that point, we have a couple of options. One, we could say, this is only one network address. We have 3 individual separate networks that we need to deal with. So we have network A, network B, network C. We could argue that we need more IP addressing space, or the other option, my friend, is to go ahead and do custom subnetting. The process of subnetting is simply taking an existing network space that we're given and chopping it up into smaller pieces. Sort of like if we had Sunset Street, for example, and we needed to break that up into smaller sections. Maybe we could have like Sunset Boulevard, Sunset Avenue, Sunset Lane, and we can break it up. All we're doing when we're doing custom subnetting is we're taking one network address space, like the 192.168.5 network, and we are going to chop it up into smaller pieces so we can make additional smaller networks. Now, unfortunately, there is a price that's going to be paid if we take a perfectly good network like 192.168.5 and we chop it up. This network, which currently has 24 bits for the network and an 8 bits over here for the host portion, in order to do custom subnetting, what we have to do is we are going to say goodbye to a few good host bits. Those 8 host bits, which are over here, we are going to have to sacrifice some of them. Did I say have to? And the answer is yes. We are going to voluntarily take some of the bits over in this host portion from the network that we're dealing with, and we are going to allocate some of those bits over towards network addressing. And effectively what it's going to do is going to make more room for network address space, and we're going to use that additional space, those additional bits, to carve out additional subnets. So let's use a practical example here. Let's say we do have a 192.168.5.0/24 network, and we have to use that major network to go ahead and create additional space. The very first question to ask us in this scenario is, how many new networks, or new subnets, if you will, do we need to create for our topology? In this example, we need 1, 2, and 3. So step number 1, I'd like you to write this down with me, is identify number of new subnets needed, because that is the very first step. Identify the number of new subnets needed. So once you've got that jotted down, I'm next going to share with you how you can calculate how many bits you need to take. I'm talking about stealing bits from the valid host bits which are currently available, and we're going to sacrifice them to network address space. And that's done through something called the finger game. Now, if you're wondering, Keith, what the heck is the finger game? You're not going to have to wonder too much longer, because we're going to play it together. I'm going to do this literally with you. So here's what I'd like you to do. I'd like you to look at your fingers, and include your thumb in that discussion. So look at your fingers, and I'd like you to imagine that your fingers are bits. So if you hold up all your digits on your right hand or your left hand, you look at them, how many digits are there? How many bits are there? And the answer for most people is going to be 5. Unless you're like my shop teacher in high school, but that's another story. So let's go ahead and use the presumption that most people are going to have 5 digits on their hand. And for this game, each of those digits represents a bit. So here's what I'd like you to do. I'd like you to go ahead and act like Fonzie from Happy Days. If you don't know who that is, I'll go ahead and walk you through this. You're going to make a fist with your right hand, stick it out in front of you, and then stick just your thumb up in the air. So with your thumb in the air, I'd like you to look at the back of your thumb, look at your thumbnail. I'd like you to imagine that somebody took a black permanent marker and they wrote right on your thumbnail the number 2. So look at it, see it. What kind of a font did they use? Is it clean? Is it sloppy written 2? But see that 2 on the back of your thumb, and here's what we're going to do. If you only need 2 new subnetworks, all you need to do is steal or take a single host bit from the current available host bits to accomplish that. So the 2 is on your thumb represents that 1 bit, and that's the formula. Now in our case, we need more than just 2 subnets. So here's what we're going to do. With your thumb still up in the air, we're going to go ahead and bring up another digit, like your pointer finger, and when you bring that finger up, I want you to double the 2 on your thumb. So that goes to 4. The number that you verbally said is the number of subnets you can create. If you look at the number of digits in the air, which are now 2, that's how many bits it takes to generate that many subnets. Just for grins, that meets our needs. All we really need to do is take 2 bits, and that'll create 4 subnets, which meets our need of 3. So let's do this. Let's start from scratch, and let's see how many subnets we could create if we stole or took 5 host bits. So the game always starts like Fonzie. You make a fist, you put your thumb in the air, on the back of your thumb there's a 2. And the next thing we're going to do is bring up our pointer finger and verbally double that number to go to 4. And bring up another finger, so we have 3 digits in the air, and double the number to 8. Bring up another digit, double the number to 16. Bring up another digit, now all 5 digits are up, and double that number to 32. And I want to remind you what the importance of this game is, what the relevance is. If you look at your fingers, you've got 5 digits in the air. That means if you take 5 bits away from the host addresses and you allocate them for network addressing, you can have 32 brand new subnets by using the address space available in those 5 reallocated bits. And this finger game that we can use to calculate the number of bits or digits on our fingers to use to create a certain number of subnets is a very valuable skill that'll come in very handy for you. So in our case, we only need 3 subnets to support this topology right here. So just as a review, let's do the thumb game once again, and we want to make sure we're going to identify how many bits it takes to create up to 3 subnets. So we play the finger game by making a fist. We put our thumb in the air. There's a 2 on our thumb. 2 is not enough. We bring up another digit. We double that number to 4. And that means with 2 bits, represented by the 2 digits that are up in our hand, we can create up to 4 subnets. So that third step is to identify number of bits to sacrifice. And I do say sacrifice because they were available host bits, and once we sacrifice them over for network addressing, they will no longer be available for host bits. So in our case, we are going to sacrifice 2 host bits because that allows us to have up to 4 subnets. 1 bit wasn't enough, and 2 bits gives us up to 4 subnets, which meets our need. And the fourth step, and this is the most important, is to go ahead and let everyone know. What do you mean, Keith? You have to let everyone know. You see, if we are going to change the rules and use 2 host bits for the network address, we need to make sure that all the devices on the network know about it. So what we're going to do is we are going to modify the mask. You see, for this network at the moment, the mask is only claiming the first 3 octets, the first 24 bits of the IP address space. But now, if we're going to use the additional first 2 bits of that last octet, we need to change the mask. And that, my friend, is how we communicate the details of using additional bits for the purpose of networking. We're simply going to move the mask that many bits to the right, and they're still going to be contiguous. So now it's going to be the first 24 bits here, plus the first 2 of this last octet. The new mask is going to be 26. Now, out of our beautiful IP address space, now we only have 6 host bits available left for host addressing, which is restricting us a little bit on that end. But now we have more address space to play with, so we can create up to 4 brand new subnets. So your exercise right now is to write out these 4 steps. And that is to identify the number of new subnets that you need to create. Use the finger game with a 2 on your thumb, with your fingers representing bits and doubling the number every time you bring up a new digit. Remember, start with a 2 on your thumb. And then once you calculate how many fingers are in the air that meet your requirements for the new number of subnets, you identify that. In our example, we only needed to take 2 bits. And the fourth step is to modify the mask to let everybody know about it. And that's moving the mask to the right by that quantity of bits. So take a moment, make sure you have those 4 steps written down. And what I would like you to do is go ahead and pause me, turn the paper over, and I'd like you to go ahead and from memory repeat those steps. If you need to peek over the other side as a refresher, that's perfectly fine at the beginning. But I want to make sure that you, on your own, know this exact process. When you've written these out and are comfortable that you understand the process that you should go through, go ahead and resume me. And I want to share with you one more technique that's really important regarding the moving of that mask, those 2 additional bits. Now here's one of the challenges that's going to come up when we move that mask from a /24, which it was, over to a /26, is that how do we actually represent that in decimal? Because when we work with IP addresses, we're putting in dotted decimal. So what does a /26 look like in dotted decimal? Well, the first 24 bits are good for the mask are 255, 255, 255. Now that's not new. What is new is how do we represent the first 2 bits of that last octet, these guys right here, for the mask that they are on? And the answer is we're going to go back to binary for that. This bit on and this bit on. So that's bit 25 and bit 26. And all these bits in the mask are now off. What would that be in decimal? Because that's how we're going to have to input it to the device we're working on, whether it's a router or a computer. And to figure this out, we already know how to do the conversion. From binary to decimal, we simply add the values. So we add 128 and 64, and that's a whopping total of 192. So for the mask in the last octet, we would put 192, and what that tells the router or the computer that you're on is that, hey, we're using a /26-bit mask. The first 3 octets are all taken for network addressing, and the first 2 bits of that last octet are also taken for network addressing. Now, I can hear it already. Some of you might be saying, oh, I don't want to have to convert from binary into decimal every single time I put some type of a custom or non-default mask on an IP address. And I'm totally with you. And that's why what I would recommend you do is create this mask values table as well. So right when you sit down to start working with IPv4 subnetting, you should definitely write out this table right here, which is the weights of the various positions for 1 byte of data. And you should also jot down the mask values for each of those positions. For example, if we had a bit on in this position by itself and nothing else, that would be a value of 128. If we take 128 plus 64, that would be 2 bits on, it'd be a total of 192. If we had the first 3 bits on, for example, it would be 128 plus 64 plus 32, which is 224. And plus 16 more would be 240. And plus 8 more would be 248. Plus 4 more would be 252. At some point, if you work with IPv4 a lot, you're going to have these values up here absolutely memorized. But until then, what you could do is this. Simply write out this table. Write the weights first, and then simply write the mask values, which the mask values are going to be 128 plus 64 plus 32 plus 16, and that's that top row right here. If we had a situation where we needed to use 5 bits for custom subnetting because we had a requirement for 32 subnetworks, and we needed to take 5 additional bits, it would look like this in binary. We take that one, that one, that one, that one, and that one. We would leave these last 3 bits for host addressing. The dividing line would be right here, and our mask value would be 248. And if you needed to, you could manually calculate that. 128 plus 64 plus 32 plus 16 plus 8. But having this table here is very, very handy. So here are the 2 things that I want you to take away from this video. Number 1, I want you to be comfortable with the idea that we are stealing, we are taking away available host bits and sacrificing them for the purpose of creating additional networks. The other thing I want to make sure you're comfortable with is quantity. How many bits do we need to take in order to create a certain number of subnets? And that's all about using the finger game. Here's what I'd like you to do. I'd like you to do a scenario where you need to create 42 new subnets. So here's my question. If you needed to create 42 brand new subnets, how many host bits would you have to sacrifice to meet the need of 42? And the cool thing is this. This concept applies to Class A or Class B or Class C addresses, because maybe you have a 10 network that's starting with an 8-bit mask, or a 172.16 that's starting with a 16-bit mask, or a 192.168.5 that's starting with a 24-bit mask. It really doesn't matter, because all we're doing is we're stealing subnet bits from the current host portion. So in a network that had an 8-bit mask, we would start stealing the bits from this octet right here, because that's where the host bits start. In a 16-bit network, we would start stealing host bits from this 3rd octet, because that's where the host bits start. And from a network that had a /24-bit mask, we would start stealing the actual host bits from the host bits portion, which in this case is the 4th octet that we would begin stealing from. The actual quantity calculation doesn't change. It's all a matter of how many bits this is going to take to create a certain quantity of subnets. So here's what I want you to do right now. Go ahead and calculate using the finger game. How many host bits are we going to have to sacrifice to network addressing in order to get 42 subnets? Go ahead and pause me right now. Go ahead and do the finger game. If you're in a cubicle and people can see you, it's perfectly okay. Get those fingers flying, starting with that 2 on your thumb. So go ahead and pause me and do that now. All right, so let's see how you did. I'm going to go ahead and I'm going to do my thumb in the air right here. And this is going to be my fist. And on the back of my thumb, I've got the number 2. So that's where we start the finger game, is a number 2 on the back of our thumb. So our goal is to get up to 42. That's how many new subnets we need. So we put our thumb in the air, we say 2, that's not enough. We bring up another finger, and we go to 4. That's not enough. We bring up another finger. We go to 8. That's not enough. We bring up another finger. That's 16. That's not enough. We bring up another finger. That is 32. And that is not enough. So if we sacrificed 5 bits for custom subnetting, we would only get 32 subnets, which isn't enough. So what do we do in this situation? The answer is you keep that one hand with all 5 digits up, and you bring up the other hand and continue to double. So on our other hand, so I'll bring up another finger there, and we go to 64, and we stop, because 64 will meet the requirement of 42 subnets. And here's how the counting goes. We have 1, 2, 3, 4, 5, 6 digits in the air. That means we need to take 6 bits. And 6 bits will create for us 64 subnets. It's kind of a funny little game, but it's a great way to consistently get that information right. How many subnets do you need to create? How many bits will it take using the finger game? And then changing the mask to reflect that. So if we're taking 6 more bits, let's apply that to changing the mask. In the case of a current mask of 8, the new mask would be 14. We're simply adding 6 bits. In the case of 16, the new mask would be 22. 16 plus 6 more. And in the case of 24, the new mask would be 30. So to represent those 6 bits, it would look something like this. 1, 2, 3, 4, 5, 6. That's the new mask. We put the dividing line right there. And the new mask would be 252. So the new mask for the second octet for this network would be 252. The new mask for the third octet would be 252. And the new mask on this network, the 192.168.5/30, that would be in the fourth octet, the mask would be 252. It's representing on each of those networks that we're stealing the additional 6 bits and allocating them for network address space. And the concept is the same for each and every one of them. In the next video, I'll walk you through how to go ahead and determine the actual values of those additional subnets. IDs for new subnets. Every person really needs a name, and our new subnets need a new number. In this video, we'll identify exactly how to identify the new subnets you create and make it a simple process. If we needed to create subnets for this topology right here, and we need to make it all fit inside of the space of 10.0.0.0/8. How many of those 24 host bits do we need to sacrifice to create up to 12 subnets? And my friend, to solve that, you simply play the finger game. So we need to steal 4 host bits. See, 3 wouldn't be enough. 3 would only give us 8 subnets. By stealing 4 host bits, we can get up to 16 subnets, which meets our requirement. So then the question is, what would the new mask be? The original mask is a /8. We're stealing 4 more additional host bits. Those are going to come out of the second octet in this example, because that's where our host bits are starting. And so if we stole an additional 4 host bits and allocated them to the network address space, what would the new mask be? Now, if you're saying the new mask would be the old mask plus the 4 additional bits, which would be 12, you are absolutely correct. That's fantastic. And now, my friends, it's time to identify what the actual subnet IDs are going to be for those new subnets. Now, by stealing 4 bits, we actually are going to have a possibility of 16 new subnets. So we're going to have 4 left over that we're not using because we only need to go up to 12. And that's perfectly fine. But what exactly are those subnets? And to solve that, this is a fun part. To solve that question of what exactly are the subnets for this guy and this guy and this guy, all we're going to do is these 2 simple rules. And let's start with number 1. We are going to, first of all, determine the block size. Now, the block size, and I affectionately refer to it as BS sometimes, just because the shock factor sometimes reminds people to go ahead and look for it. The block size is nothing more than the least significant bit of the new mask. Whoa, Keith, stop the truck. What do you mean the least significant bit of the new mask? Well, if you take a look at these 4 bits that are on, and we're looking at this second octet here, if you look at these 4 bits in the mask, which one is the least significant, has the lowest value? If we look at each of these bits, the very least one, the one that has the lowest value, is this guy right here, and that is the new block size. And what I'm going to have you do, if you've written this out, which I would encourage you to do, I would have you put a square around that number. So wherever the least significant bit is of the mask, I'd like you to put a block around that value. And that is your block size. In this case, it's 16. If we were stealing 5 bits, it would be 8. If we were stealing 7 bits, it would be a 2. Now, how is that going to help us? What we're going to do is we're going to begin at 0 and then simply add the block size. So for step number 2, in this example, let's go ahead and take 0. Now, that's really easy to get to. That is our first subnet, and sometimes it's called subnet 0. So that's our very first subnet, is subnet 0. And then for our next subnet, we simply add the block size. So it's 16, so we add 16 to this. That is our second subnet. And the third one, we're simply going to add the block size again. So plus 16 more is 32. And then we're going to add 16 more again. That makes 48. And our next one's going to be 64 for our fifth subnet. Again, we're simply adding 16. And we simply add and add and add and add. And if we added 16 again, it would be 80. So that'd be our sixth subnet. So now as we look at these subnets, what's the problem? Well, they don't really look like subnets, do they? They just look like a digit or a couple digits, and they're not really in the format of an IP version 4 address. So here's how we complete the picture. See this first network of 10.0.0.0? The new mask is going to be 12. All we're going to do is we're going to bring that same network that we started with up, 10.0.0.0. We have the new mask /12, and guess what? That is subnet 0. That is our first network. And that means that in this second octet right here, we haven't added a block size to it. That's our starting point. So subnet 0 looks like the original network with the new mask. For the next subnet, we're going to add that 16. So it's going to be 10.16.0.0/12, and that's our second network. And then 10.32.0.0/12. And that's our third network. And then 10.48.0.0/12. And it's important to put the mask on there so that you can communicate exactly how many bits are being used for the network. And then we have 10.64.0.0/12 and 10.80.0.0/12. And if we continue this process, we would actually get up to a point where we have 16 possible new subnets because of the 4 bits that we're stealing. So let's do another example, and I want to do it from start to finish each time so that you get in a rhythm or a pattern of exactly how to do this. Let's say that we want to have this network here, still 12 subnets, and we want to make it all fit in the address space of 10.50.0.0/16. That's our starting point for all of our new networks. We're still going to be stealing 4 additional bits because the actual quantity of subnets hasn't changed. Our new mask is still going to look like this with the dividing line right here, except now we're starting to steal against the host bits, which are in the third octet instead of the second octet. And that's because the 16 bits we're starting with indicate our starting point for the already allocated network bits. So here's what I'd like you to do. I'd like you to do these 2 steps. This is your expert exercise right now. I'd like you to determine the block size based on us using 4 additional bits for custom subnetting. And I'd like you to list out on paper the first 6 subnets that we would be using on this topology. All right, for those of you who are able to do this on your own, that's great. This does take a couple of practices to get the hang of it. So our subnets are going to be right here, determine the new block size, which is 16. So you're going to put a block around that to remind you that that is the block size. You're going to begin at 0, and here's our subnets. They are 0, and 16, and 32, and 48, and 64, and 80, and 96. 1, 2, 3, 4, 5, 6, 7. Okay, so that's the first 7 subnets. Now, what exactly are those going to look like as far as network addresses? Well, the first one is going to be 10.50, because those were already locked in stone before we got there. That's what we were given. And what we're doing is we're stealing the first 4 bits from the third octet. So subnet 0 looks like the parent, I call it the parent network, and it looks like the same exact network except for the longer mask. The mask was 16. We're stealing 4 more bits. The new mask is now going to be 20. The next subnet is going to be 10.50.16.0/20. And the next one is 10.50.32.0/20. And it's just going to continue all the way down. So in a topology diagram like this, we might just say in the documentation that this is the 10.50.x.0/20 network. Then for these subnets, instead of writing out the entire subnet address, we might just put the value of x. For example, this is subnet 0, this is subnet 16, this is subnet 32, this is subnet 48, etc. And then somebody looking at the topology could say, oh, this is the network 10.50.0.0/20, this is network 10.50.16.0/20, and so forth. This time, let's mix it up a little bit more, and this will give us another opportunity to review the process and make sure that we have it down pat. In this case, let's say we don't need 12 subnets. Let's say we just need 6 subnets, and we want to make it all fit within 25.35.65.0/24. So that's our starting point. So my question is, when we're given this, the very first thing that you'd have to do is what? What's our very first step? Now, when I look at this, it's like a game. It's like we have to find out some value first. And the first thing we really need to calculate is, okay, how many host bits do we need to take to create up to 6 subnets? And the answer is 3. So we play the finger game, we determine that we need to take 3 bits, and we are going to change the mask by increasing it by 3. So it would visually look like that. All the rest of the mask for that octet, in this case the 4th octet, would be zeroed out. And the new mask, because we're using 3 more bits, would not be a /24. The new mask would be a /27. So that's all the finger game in calculating what the new mask is going to be and how many bits we took to get there. And now, my friends, what I would love you to do is these 2 things. Determine the block size, and then secondly, I'd like you to identify all 6 subnets that we would need for this topology. So pause me right now, take a moment, work through that, and then when you're ready, we'll compare notes. So here's the process that I would go through in solving this. I literally would. If you were watching me sitting at a desk and actually going through this, I would have written out the weights. Now, I do have a lot of it memorized, but on an average day, I would write out the weights, and I'd say, okay, great, my block size is 32, because that's the least significant bit of the mask, the new mask. And I would say my subnets are 0, because that's where we always start. And the next subnet would be 32 more. And the next subnet would be 32 more. And the next subnet would be 32 more. And the next subnet would be 96 plus 32. And we can just add that up. 96 plus 32, that'd be 8. And that'd be 12, which is 128. When in doubt, do the longhand math to make sure you have the numbers right. And these are our new subnets. So over here, for example, in our topology, we could just write out, this is the 25.35.65.x/27. And this is subnet 0, subnet 32, subnet 64, subnet 96, and so forth. So I'd like to do one more with you, and I'd like to go a little bit abstract. Let's say we have a network that is a /16. So forget about the first 2 octets. Whatever they are locked in stone. We are dealing with now the 3rd octet as we're going to start stealing bits. And let's say for the purpose of this discussion that we need to steal 5 bits from host addressing in that 3rd octet. And that would allow us to create up to 32 subnets. So our dividing line is right here. And my question for you is this: what would the new mask be if we're stealing these 5 bits? And what would the first 5 subnets be? And again, it really doesn't matter about these first 2 octets because they're going to stay the same for the entire discussion. It's really all about the 3rd octet where we're splitting and slicing and dicing the bits for subnetting purposes that we need to pay attention to. So again, what's the new mask and what are the first few subnets? Go ahead and pause me and work those out right now. What is really cool about this process is that it's the same. We're going to go ahead and first of all determine the block size. In this case, the least significant bit is in the position of 8. So that's our new block size. The subnets are going to be 0. And again, we're in that 3rd octet because the first 2 are already chewed up. So our first subnet is going to be the 0 subnet. The next subnet is going to be the 8 subnet. and then we're going to have 16. And then this is for some, this is a little bit of a challenge, but only add 8 again. Don't go doubling. This is just adding the block size, adding the block size, adding the block size. So this would be 24, and this would be 32. And of course, we have another octet out there, so we'd have to hang that guy off as well. And then the new mask, what's that going to be? The original mask was 16. We're taking 5 additional bits. So 16 plus 5 is a /21. And if we had to write out that mask in dotted decimal, it would be 255, which means the first octet is all network. 255. The second octet is all network. That was that way before we got here. And what we've done is we've stolen 5 bits from that third octet. And to represent that, it would be 128 plus 64 plus 32 plus 16 plus 8. Or, and we have 248 already written for us, we could just say it's 248. Any way you want to get there is perfectly fine. It's just math. And then the last octet is all host bits. So the host bits available are the 3 host bits from this third octet plus all 8 bits from the last octet, for a total of 11 host bits available. In our previous video together, we identified the individual subnets that can be created, and in this video we're going to focus on the valid hosts that would fit on those subnets. So to do that, let's go ahead and use an example of this topology. We have 3 subnets that are required so far. Let's add a few more. Let's add a network out here, 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 and here. So we'll need a total of 1, 2, 3, 4, 5, 6, 7 subnets. So let's say we have a /24 network to begin with. So x.x.x.0/24. Now, do you get it that these first 3 numbers are going to be the same across the entire board if this is our major network? So we're going to start from that point. We're going to start stealing bits from the host portion, which is the last 8 bits. So by using the finger game, we can calculate that we need to steal 3 bits. That will give us up to 8 subnets, which is enough for our topology right here. So our new dividing line is right there. Our block size is 32, and our subnets are going to be subnet 0, subnet 32, subnet 64, subnet 96, subnet 128, subnet 160. Again, we're just adding the block size to each one of these. Subnet 192, and subnet 224. We're only going to need 7 of them. So over here, we could have this be subnet 0, this could be subnet 32, this could be subnet 64 right there, this could be subnet 128, subnet 160, subnet 96, I didn't mean to leave him off, and over here, subnet 192. So those are our subnets, and of course, the first 3 octets would be XXX, meaning they would be whatever they were over here, followed in the last octet by this value. So let's say we've identified these subnets, we know where we're going to put them, and we want to go and configure an interface. For example, let's take a look at serial 0/0 on router 2. We go into interface configuration mode, we want to configure the actual IP address, and then we realize, oh my goodness, what are the valid IP addresses that are on subnet 128? And the focus of this nugget, this video, is to go ahead and walk you through the very straightforward process of identifying exactly what the valid IP addresses are for subnet 128. And the process is right here. You're going to start by listing the subnets. So here we have all 8 subnets. And again, we're going to use the block size to determine our subnets. Once we have the subnets listed, and we're interested, for example, in the range, let's go ahead and take subnet 128 as an example. The very first host, the first valid host IP address on a subnet is going to be that subnet plus 1 in the very last octet. Now in this case, we're already in the very last octet right here. So for the 128 subnet, the very first host is going to be 129. So I'll call this column right here first host. Now I want to ask you a question. If 129 is the first host, do you think 130 is also a valid IP address on this subnet? If you're saying, yeah, Keith, it sounds like it would be. It's right next to it. How about 131 and 132 and 133? And if you look at the numbers, everything that is lower than 160 is part of the 128 subnet. If we go high enough, we're going to bump into subnet 160. And the reason that's important to know what the next subnet is that the range of IP addresses on the 128 subnet will never go as high as 160. Why is that? Because 160 is the next subnet. So if we wanted to calculate all the valid IP addresses on the 128 subnet, the very first host would be the subnet plus 1, and the very last host is going to be the next subnet right here. I'd like you to read this with me. The last host is going to be the next subnet minus 2. So if this guy's 160, if we subtract 2 from that, the last host on the previous subnet is going to be 158. Now, the first knee-jerk reaction is, why? Why do we have to subtract 2? Why can't we just use like the next subnet minus 1? And the reason for that is the next subnet minus 1 is the broadcast address for the previous subnet. So the first host is this column. The last host is right here. And the formula for that is the next subnet minus 2. And the broadcast address is going to be the next subnet minus 1, which is 159 in this case. So what that means to us, if we want to configure the IP addresses here on subnet B, which is more specifically subnet 128, the valid IP addresses that you and I could choose to use for any device on this network, and I'm laughing because there's only 2 here, but the range of IP addresses could be anywhere between 129, so x.x.x.129, through 158. We couldn't use 128 because that's the actual street name all by itself. That is the subnetwork address. First valid host is 129, last valid host is 158, and regarding this subnet right here, the broadcast address that we would associate with this subnet is 159. One more IP address higher, and we're looking at the next subnet. So let's you and I do another exercise. For our requirement, let's say that we have a /16 to begin with, and let's say we have a requirement to create 15 new subnets. What I would like you to do is I'd like you to go ahead and list the first 4 subnets and their ranges. The ranges for a valid host address on those first 4 subnets. And for bonus points, go ahead and include the broadcast address for each of those subnets as well. Go ahead and pause me and do that right now. All right, welcome back. I'm curious, how did you do? Were you able to put all the pieces together? Here's how I would approach this. I'd say, first of all, we have this /16 network. Great. We need 15 new subnets. So, of course, we're going to do the finger game to identify how many bits we have to take away from host addresses to create at least 15 new subnets. The answer to that is 4 fingers, or 4 bits. And that new mask would look like this. There's our dividing line. There's our block size of 16, and the first 4 subnets would be 0 for subnet 0, 16, plus 16 more is 32, plus 16 more is 48. Now what's different about this than the last example is we are working in this 3rd octet right here. So this byte of data that we're cutting into, the host portions, represents the 3rd octet. So our new mask, it was a 16, so the new mask is going to be a /20. And I'm going to bring those subnets down here. We have x.x representing the first 2 octets. We have .0 and x.x.16 and x.x.32 and x.x.48. Those are our first 4 subnets. Now, because we are in the 3rd octet, we have another 8 bits to represent over here that are all host bits. So a total of 12 host bits. These 4 here from the 3rd octet, plus all 8 bits from the last octet for host addressing. Now I did throw you a little bit of a curveball because we are no longer in the last octet. We are in the 3rd octet that we're actually stealing bits from. So if we wanted to calculate the first valid host address on these subnets, how would we do it? And the answer is the same exact way that we did it before. Our first task is to list the subnets. Well, here's the first 4. That's done. The first host is going to be the subnet +1, and we add that +1 to the last octet. So this network of x.x.0.0, the first valid host, I'll write first here, is going to be x.x.0.1. That's our first valid address. The first valid host on the 16 subnet is going to be 16.1. The first valid host on the 32 network is going to be 32.1. And The first valid host on the 48 network is going to be 48, and you got it. We're just simply going to add 1 to the last octet, 48.1. We've got the first valid IP address on each of those subnets. The next question, what is the last valid IP address? Or we might even want to go for the broadcast address first, if you want, and then we could simply subtract 1 more from that for the last. So let's say for the 0 subnet, that's right here. Our first subnet is subnet 0. The first valid host address is 0.1. And I think the broadcast address is going to be the next subnet minus 1. You know why I think that? Because that's exactly how that works. Right here. The broadcast address is the next subnet minus 1. So if we wanted to look at the next subnet, which is 16.0, what is 16.0 minus 1? It's going to look like 15.255. And let me show you that in binary. In the third octet, we have 4 bits that are on. And then in the last octet, we have 8 bits that are on. So that is 15, and that is 255 right there. And our mask is right here. So my question is, what happens if you add 1 more, plus 1 right here? Well, all of these are going to carry over. So the plus 1 is going to topple all of these to zeros. This is going to turn to 16 because they're all going to topple over. And that's the binary behind it. So 16.0 minus 1 is 15.255. You simply put 255 for the last octet, and you take this number and say minus 1. So the next question is, okay, what's the last valid host on the 0 subnet? Well, it's the next subnet minus 2. So if the broadcast is 15.255, this last IP address is going to be 15.254. So our range of valid IP addresses on the 0 subnet is going to be whatever those first 2 octets are, 0.1, through whatever those first 2 octets are, 15.254, with the broadcast address of 15.255. Let's go ahead and do that same game again, and let's do it for subnet 32. And we can follow these exact steps. So on the 32 subnet, the first valid host is 32.1. The last valid host is going to be the next subnet, which is the 48 subnet minus 2. And minus 2 would be 47.254. And the broadcast would be 47.255. And then the next subnet, of course, is 48. So here's our first, here's our last, and here's our broadcast address for the subnet. For this next one, let's go ahead and use a /8. So our network is x.0.0.0. Our host bits are going to start in that second octet with a /8. And let's say we need to create 120 new subnets. So with the finger game, we get our thumb out and we start counting 2, 4, 8, 16, 32, 64, 128. I have 7 bits or 7 fingers up that represent that's how many bits it would take to create at least 120 new subnets. So our new mask is going to be 7 bits into that second octet right there. So there's the dividing line. So our new mask is going to be 7 bits above and beyond the 8 bits we started with, which is 15. That new mask would be represented in dotted decimal as 255 dot and 254 for that second octet, which simply means that the mask is taking the first 7 bits of that second octet for the purpose of network address. So let's go ahead and list our subnets and the ranges. Now, we can have a whole bunch of subnets. In fact, we're going to have the ability to have up to 128 subnets. I don't want to list all 128, but let's go ahead and list like 4 or 5 of them to get the feel for it. So the first subnet is going to be subnet 0. And then our block size, because it's a 2, the next subnet is going to be 2. And then add 2 more, and add 2 more, and add 2 more, etc., etc. So that's our block size, and that's why we're adding that. And those are our subnets. So our subnets are going to be x dot with that x being whatever it was. It could be a 10, it could be a 40, it could be 195. Whatever it is, it's going to stay that way. Now, because this is the second octet where we're doing our custom subnetting, we still have 2 more octets of zeros, so we'll put them in as well. So there's our first 5 subnets. Subnet 0 would be our first, and then we have second, third, fourth, and fifth. We could also refer to them as subnet 2, subnet 4, subnet 6, etc. So now, let's go ahead and let's determine what the actual valid ranges are for each of these subnets. In fact, let's go ahead and just pick on subnet 2 just for a moment. And what I'd like to do is for subnet 2, let's identify the first host, the last host, and the broadcast address for subnet 2. The rules are exactly the same. We've listed our subnets. That's already done. We've got 5 of them right here. For the first host for subnet 2, it's going to be one more than the actual subnet value itself. So the first host is going to be x.2.0.1. And that's the first valid IP address on subnet 2. Now the last valid IP address is going to be the next subnet -2. And the broadcast is going to be the next subnet -1. Whichever one you want to do first, you absolutely can. So let's do the last address. That would be x.4.0.0 -2. So that would look like this. x.3.255.254. And that is the last valid IP address on subnet 2. And the broadcast address is going to look just like the last IP address, except it's going to be 1 greater than. So the broadcast address is 1 greater than the last IP address, and it happens to be 1 less than the very next subnet. Let's do one more. Let's go ahead and do it for subnet 6 right here, which is our 4th subnet. And what I would like you to do is go ahead and pause me right now. I'd like you to write out what is the first valid host for this 4th subnet, and what is the last valid host, and what is the broadcast, using the same exact process that we just went through together. So pause me right now. When you're done, unpause me, and we'll compare notes. So for this 4th subnet, which is subnet 6, the first valid IP address is going to be x.6.0.1. It's the subnet +1. The last valid host is going to be the next subnet -2. So that next subnet value is x.8. So it's going to be x.7.255.254. That in measurable terms is the next subnet -2. And our broadcast address is 1 less than the next subnet. So that would end in .255. It'd be x.7.255.255 for our broadcast. And that's it. What we've done in this video together is we've identified how we would go about identifying not only the subnets, but also the valid IP addresses of hosts that could be in those subnets. Now, what we haven't yet done is we haven't identified how many hosts will fit in a given subnet. Now, I suppose we could do this. We could say, well, the first host is X and the last host is Y, and we could manually count between X and Y inclusively to figure out how many individual IP addresses are there in that subnet. But there's a much better way just to calculate raw quantity, and that process is this. Number 1, we're going to identify the number of host bits available. So in our topology, let's say we ended up with a /27 mask. So we have a /27-bit mask, and my question is, how many host bits are available that the mask didn't take and allocate for the network address? So if you're thinking, well, Keith, let me think about this. We have a 32-bit IPv4 address. We are using 27 of those bits. That would leave exactly 5 bits available for host addressing if we're using this mask. So that's our first step, to identify how many host bits we have to play with for that subnet. The second thing we're going to do is we are going to use the finger game. And again, our fingers, our digits, are representing the actual bits. In this case, however, our fingers, our digits, are representing the 5 available host bits. So we're going to stick our thumb up in the air with that big old 2 on it, and we're going to say 2. And then we'll bring up our second digit and say 4, the third digit and say 8, the fourth digit and say 16, and that fifth, and that's our goal, by the way, that fifth digit in the air, and we'll say 32, and that, my friends, is very close, not exactly, but close to the number of hosts, valid host IP addresses in that given subnet. Now you might be saying, okay, Keith, what do you mean it's close? It's either, this is math, it either works or it doesn't work. Well, it is true that if we have 5 bits, we have 32 different combinations. However, not all of those are valid host addresses. For example, with a /27, we know that we're stealing the first, second, and third bits out of that 4th octet. So right here is the 24-bit boundary. There's 25, 26, 27. So here's our new boundary line, if you will, between the network and host bits. Network on the left of the blue line, host bits on the right. So here's our 5 host bits right here that the mask didn't take. So for a /27, here's the block size right there, 32. We know the subnets are 0, 32, 64, 96, and so forth. And the first 3 numbers, they are going to be the same on every single one of our subnets. It's this last octet where we're slicing and dicing. And the new mask, of course, would be /27. So let's pick an example here. Let's say that this subnet 2 is going to be subnet 64. So this subnet right there. So what is the first valid host? Well, Keith, the first valid host is the subnet, and it's the subnet plus 1 more. So the first valid host would be 65. Excellent. So that's the first valid host. What's the last valid host? Well, the last valid host, as we've learned, is the next subnet minus 2. So if the next subnet is 96, the last valid host on this 64 subnet would be 94. And that is our range. And the broadcast address, I'll put B for broadcast right here, would be 95. So the reason I point that out is that this 32 is all the possible combinations we can get with 5 bits. However, we cannot, I repeat, we cannot assign the actual subnet address to a host interface like a router interface or a printer or a PC. It won't allow it. It'll say, hey, this is the actual subnet. There's no bits that are on in the host portion. We have to have at least 1 bit of the host portion that is on for it to be a valid IP address that we can assign to an interface. So what that means is we have 32 minus 1 for the subnet, which we cannot assign to an individual interface. And the other one that we cannot assign to an interface is the broadcast address for that same subnet. So we're also going to do minus 1 based on the broadcast address. And for that reason, when we calculate the number of hosts available on a subnet, we're going to play the finger game, but when we get our result, we're going to go ahead and subtract 2. And that's because we cannot use the subnet itself, that subnet address, nor the broadcast as a valid IP address on an interface. So I'd like to do one more example with you on that. And that example is this. Let's say we have a /30. My question for you is, how many valid hosts could we put on a subnet that had a /30? Now at this point, I want you to go through this process. I'd also like you to take a moment right now and pause the screen and write down these 3 steps regarding how to exactly calculate the quantity of hosts on a subnet. So go ahead and pause me, write these 3 steps down, do the math for a /30, and then resume me and we'll compare notes. Well, our first step on this is to count the number of host bits available. Well, 30 bits are being used for the network. That leaves only 2 bits for host addressing. So the answer to that is 2. We're going to use the finger game with our digits representing host bits. So we'll put 2 fingers up in the air and we count verbally to 4. That's our result. And then we subtract 2 because we can't use the actual subnet or broadcast address on an actual interface. So minus 2 equals a total of 2 possible IP addresses for valid hosts on a /30 network. I'd like to start off this by taking a look at a router interface. And here's the IP address currently configured on that interface. It's 42.255.74.251, and the mask says that the first 22 bits are all being used for network addressing. So that's 8 bits there, plus 8 more, and 6 bits. So 252, the binary representation of that would be 1, 2, 3, 4, 5, 6, 0, 0. And there's our dividing line. So the last 2 bits of this octet and the final octet as well, which is all zeros, are all available for host bits. What if we're given an IP address like this, that's sitting on some subnet, and we are asked to reverse engineer it and determine from that IP address what the actual subnet is that this client is sitting on? So as we look at where we're slicing and dicing, we know that the first 2 octets for sure are all the network address. And we have 6 bits into this 3rd octet. So the mask would look like this. 1, 2, 3, 4, 5, 6. There's our dividing line, and these last 2 bits of the mask would be zeros. And just to be sure, we could double check. So we have 16 up to right here. Then we have 17, 18, 19, 20, 21, 22. And that is correct. Also, the mask value showed 252, which is another reinforcer that we've got the mask correct. All right, so how do we reverse engineer this? So here's our process. Item number 1, identify the block size. We know how to do that. We're looking at the least significant bit of the mask. It happens to be right there. The block size is a block size of 4. Now what we could do is we could say, okay, the block size is 4. Our subnets are 0, 4, 8, 12, 16, 20, etc. But check it out. We are going to have to list a whole bunch of subnets before we're even going to come close to where this host is in that third octet. So instead of having to write out the dozens and dozens of subnets to get to the range we're looking for, what we're going to do is we're going to go to step number 2, which is a shortcut. What we are going to do is we are going to divide the last network octet by the block size. What I mean by this last network octet is the octet in the IP address where we're slicing and dicing, where that mask is ending. So in the 74, what we're going to do is we're going to take 74 and we're going to divide it by the block size. So our block size is 4. It's simply this, 4 into 74, just like that. So the block size into that octet. And then we just do the math. So 4 goes into 7 one time. There's a remainder of 3. We bring down the 4. 4 goes into 34 8 times. So 4 times 8 is 32. So we bring that down. We have a little bit of a remainder, and the decimal point would go right there. And here's the cool thing. I don't care, and we don't care what that remainder is. All we were really after is how many times does this block size go into that octet? The answer, my friend, is 18 times. Right there. That's the winner. And that's step number 2. Now, step number 3, all we have to do is take that result of 18 and multiply it by the block size. And what that's going to give us, that, my friend, is going to give us the subnet that this customer is sitting on. So let's do it. 18 times 4, I'll do it longhand here. So 8 times 4 is 32. 4 times 1 is 4, plus 3 more is 7. That, my friends, is the subnet that this customer is sitting on. And now all we have to do, step number 4, is write it out. So I'll write it out in blue over here. The first 2 octets are 42.255. Those aren't going to change. But for the third octet, the actual value of the subnet is 72. And then everything after that is going to be zeroed out. So if we were working in the second octet, it'd be the same concept. Everything to the right is going to be zeroed out. And the mask we're going to put on here is 22. So we could say, in measurable terms, that the host that has this IP address, 42.255.74.251/22, is on the 72 network. Because it's literally true. Now let's take it one step further. What if we wanted to identify what the valid IP address range is for the 72 subnet? How would we do that? Now if you're saying, oh wait, Keith, I got it. We're simply going to identify these subnets. So this is the 72 subnet. The block size hasn't changed, it's 4. That means our next subnet is going to be 4 more, and that's going to be 76. And the one after that is going to be 80, and so forth. So to calculate the range for the 72 network, the first valid host, I'll put F right here for first, is going to be x.x.72.1. The last valid host on this 72 subnet is going to be the next subnet value minus 2. So to do that, when we're in this third octet, it's going to be x.x.75.254. That's the last valid host. And the broadcast address for that 72 subnet is going to be x.x.75.255, which is one below the next subnet. And then we're off to the next subnet, which is subnet 76. So that's the process. Now, another really cool way that we could verify that that really is the 72 network that the customer is on, or in this case, the router is on, let's bring back the router for a moment, and we'll do a show IP route. If we look at the routing table for this router, it knows exactly which network it's connected to from a routing perspective, and sure enough, it's 42.255.72.0/22. If we plan ahead a little bit, the implementation or deployment of whatever we're going to be doing is going to go better based on the planning we did. And the same holds true with IP addresses and assigning IP addresses. And with IP addresses, we have different ones that we can choose from. We have Class A's, Class B's, and Class C's, and those are easy to identify based on the very first octet of the IPv4 address. And we also have a special class of IPv4 addresses for multicast. That's when we want to have traffic go from one source to a group of individuals. And the Class D multicast addresses are easy to spot. They begin their first octet with 224 through 239. And then we also have a Class E address, which is experimental. And so out of all these address spaces for unicast traffic, we're going to be using a Class A, B, or C address. And within those classes, we do have some restrictions. For example, the 127. Anything that starts with 127.anything, it's a reserved address. Any device that has an IP address that begins with 127.anything thinks it's itself. So the 127.anything address can't be used to route traffic between two computers because every computer thinks that's them. Another decision point is if we're going to use private IP addressing inside of our company, based on RFC 1918, we have choices there as well. And if we chose for our company to use the 10.x network addressing scheme, these classes of addresses, A, B, and C, have some default masks. And if we play by the rules, we're going to keep the original masks, and that's referred to as classful, or classful networking with IP addresses. Or, if we couldn't care less, we would be following a train of thought referred to as classless, which is what most of the internet does today. And an easy way to remember that is classless means we couldn't care less about the defaults. We'll use whatever mask we want to based on how we're carving up our network. Which means that if we needed to carve up our network and we needed a subnetwork here and another subnetwork here, we could take the 10 network, for example, and use a different mask and do custom subnetting. So this could be the 10.1 subnet and the 10.2 subnet and so forth. And we could also use different mask lengths at different points in our network. So maybe up here we're using a /24, and maybe on another part of our network over here in the branch office, we're using a /27. Because we don't need as many host addresses out there. And when we use different network mask lengths, that's referred to as VLSM for variable length subnet masking. And when we're using variable length subnet masks, and we're not following the defaults, we'd use a dynamic routing protocol that is classless, that can understand that there's different network lengths and different masks at different points in the network, instead of assuming that we're going to use the exact same length of mask or a default mask everywhere. So early routing protocols like RIP version 1 was an example of a classful routing protocol that couldn't handle a variable length subnet mask. And that is one of many reasons why RIP version 1 is rarely ever used. Another important aspect in our planning would be to summarize networks. So in our organizations as well as on the internet, we can go ahead and summarize groups of routes together and then train our routers how to get to those locations. So here is an example. Let's imagine we have a couple hundred routes that begin with 23.45, and then we have a route for .1, .2, .3, and they're all 24-bit networks. Instead of having a couple hundred routes in a routing table, we could summarize those by saying, you know what, we have a whole bunch of routes that all begin with this. So we could create a summary that says 23.45.anything, and then with a mask, identify that we're talking about the matching on the first 16 bits. And then in a routing table, we could tell the router, hey, to get to 23.45 anything, go ahead and use your friend R2 or whatever the next hop router is as the path to forward packets in the direction of any of those networks. And this notation here at the end, which is identifying how many of the bits are representing the network in the summary, that's also referred to as CIDR notation. CIDR is an acronym for Classless Interdomain Routing. So when we look at an IP address, whether it's a subnet that we've created or whether it's a summary we've created, this number here, the /16, which represents the number of bits that we're focused on here for the network, that's referred to as CIDR notation. Classless interdomain routing. Once again, we could care less about the class. We're summarizing a group of networks into a single statement. And the concept of summarizing applies to both IPv4 addresses and IPv6 addresses. And once we identify and plan for what our subnets are going to be on the networks, we can then apply the IP addresses. And there's several options. We can do it statically, and we just manually hard code the IP address that we want that device to use. However, that's fairly tedious if you have lots and lots of systems. So a dynamic option for assigning IP addresses is DHCP, the Dynamic Host Configuration Protocol. And with DHCP, we'd have a server on the network with a pool of IP addresses, and then clients would find those servers, request an IP address, and then use an IP address assigned by the DHCP server. And DHCP can be applied for both IPv4 or IPv6. If we want to reserve a specific IP address for a specific host, we can do that with a DHCP reservation that saves that specific IP address for a specific host. Now, if a client is configured to use a DHCP server but can't find a DHCP server, there's also a fallback, and that is to use a self-assigned address from the automatic private IP addressing scheme. And usually if we look at an interface that shows that IP address, that means trouble. Something went wrong. But that's a dead giveaway that automatic private IP addressing has been used on that system. And with IPv6, it uses multiple IP addresses, not just one. And one interesting trick that IPv6 has on a system, it uses what's called EUI64. And the EUI stands for Extended Unique Identifier. And what it will do, it will take a portion of the layer 2 address, the MAC address on Ethernet, and use it as part of its IPv6 address. I was thinking to myself, what could we do as a challenge to help verify that we understand the concepts of IP addressing for IPv4 as well as subnetting? So I thought to myself, well, if somebody's gone through most of the nuggets in this module, and they've been following along and doing the assignments and practicing along with me as I've invited you to, I bet you they could pull off this scenario right here. So here's the topology we're going to go ahead and use. We have two routers, R1 on the left, R2 on the right. There are a total of 3 networks. There's a network here, there's a network here, and there's an IP network here. And what I would like you to do is take the scenario where we have a network of 10.20.0.0 with a 16-bit mask, and we're going to do custom subnetting, and we're going to extend the mask out to 21 bits in length. So in one of our nuggets, we identified on how to do that and also how to identify the new subnets that would be created. And then as far as applying those subnets, I'd like to go ahead and apply the first subnet here, the second subnet here, and the third subnet right here. Also, for the routers, for their IP addresses on the new subnets, I'd like to use .1 in the last octet for R1 and .2 in the last octet on the interfaces for router 2. And the PCs are already configured and ready to go. They're just waiting for the rest of the network. So what I'd like you to do is take some time and calculate what those new subnets would be and also what the IP addresses would look like on the router interfaces. I'd invite you, when you're sitting at a computer and you're logged on to CBT Nuggets and you've got the link for the virtual lab, to go ahead and launch the lab and actually practice putting in the IP addresses you believe to be correct for each of these subnets. And one of the things that we'll want to know as we apply IP addresses is what vendor or what type of router are we using, because the commands are going to vary slightly based on the type of vendor that we're using. So because router 1 and router 2 are both from Cisco systems and they're Cisco routers, let me give you a brief walkthrough of how we'd apply an IP address to a Cisco router. We type in config-t, that's short for configure space terminal. That would put us into what's called global configuration mode. And then once we type in interface space gig space 1/0 and press enter, that puts us into a logical place called interface configuration mode for that specific interface. And it's at that point we can go ahead and configure an IP address on that interface. So we would put the IP address here. These 4 octets are the IP address. So R1 is always going to end in .1 in this topology, and R2 is always going to end in .2. And this octet right here is going to have our custom subnet value. And then the following number here is the network mask. So we know what the mask is going to be. It's a /21, but on a Cisco router, we're going to enter that as dotted decimal. So whatever the dotted decimal equivalent is, a /21, that would go right here. And once we press enter and have configured the IP address, we can type in exit to exit out of interface configuration mode. And then on this router, we can go to interface gig 20. And then we can do the similar treatment for router 2 with its gig 1/0 on the right and its gig 2/0 here on the left. So what I invite you to do are 3 basic things. Number 1, before we do the walkthrough together, consider taking some time and actually calculating the subnets and the IP addresses involved on your own, and then you can compare them to what we do together as we proceed through the nugget. Secondly, if you're at a computer logged on to CBT Nuggets and you want to practice putting in the interface IP addresses on the router, you certainly can. Because if you're logged in from a computer, there's a little link for the virtual lab that you can click on that will launch the lab and give you the opportunity to go to the interfaces and put in the IP addresses and verify it that way. And the third thing, besides having fun, is that if you ever run into some aspect where you're not quite sure of it, please go back and revisit the nuggets in this module to reinforce the concepts so that you feel confident about understanding the basics of IP addressing and subnetting, and with this lab, a little bit of hands-on implementing IP addresses. And for those of you who plan to work this through and then test it before going through the rest of the walkthrough, one simple way to verify that everything is working is that when you're done with the configuration on router 2, you could exit configuration mode and do a ping out to PC1's address at 10.20.0.11. And if that works, that's a way to verify that your configuration is correct. To solve this, one of the first things we could look at is the new mask. It's a /21.
which means that we have a block size of 8. So if the original network is 10.20 with the 16-bit mask, the first two octets are going to stay the same. And the first subnet, subnet 0, is going to have a 0 there. The next subnet will be incremented by the block size in that same octet, which would be 8. And the third subnet is going to be 16. Once again, incrementing it by the block size. And then we're going to have a trailing 0 to make the 4 octets of a network address. And those are all going to be /21. So subnet 0 is going to be the first subnet. Subnet 8 is going to be our second subnet. And subnet 16 is going to be our third subnet. So the IP address on router 1 on this 10.20.0 network is going to be 10.20.0.1 with a 21-bit mask. However, when we implement that mask, because we can't use a /21 here, we have to do dotted decimal. It's going to be 255.255. And then 248, which represents 5 bits from that third octet being used for network addressing, followed by a 0, and that's the dotted decimal equivalent for a mask of /21. So on R1, the interface IP address would be 10.20.0.1 with that mask. On the gig 2/0 interface, it would be 10.20.8.1 with a 21-bit mask. On R2, the interface here, gig 2/0, would be 10.20.8.2 with the same mask. And then gig 1/0, connected to subnet 3, would be 10.20.16.2 with a 21-bit mask. And if those IP addresses are all implemented correctly, these PCs, PC1 and PC2, have already been configured to use R1 and R2 respectively on their local networks as their default gateway. Also, there's a dynamic routing protocol already running on R1 and R2. So if the IP addresses are put in correctly, there should be full reachability between all these subnets, and PC2 should be able to ping PC1 and vice versa. So I'm using our lab gear at the moment, so if you launch the lab from a computer, it'll look exactly the same as this. So at the moment, we're on router 1. Also, if you need a peek at the topology again, if we minimize this terminal window, it's right there if you ever need to look at it. So let's go ahead and bring back the terminal window. And here on router 1, we'll type in config space T to go into configuration mode. Then we'll type in interface gig 1/0 and press enter. So typing int is a shortcut for typing the whole word of interface. And then here in interface configuration mode on R1, we'll give it the IP address of 10.20.0.1. Had to think about that for a second. And then we're going to put the 21-bit mask in dotted decimal, which is there's 8 bits of it, there's 8 more, and there is the last 5 for that third octet, .0, and that is the IP address. And what it loved about that was the fact that, Keith, you got to follow the syntax. And so if you have a problem or you didn't do the syntax correctly, it's going to bark at you. So what I failed to do is type in the word IP address. I got so excited about the IP address, I failed to type in the word IP address. So I'm going to fix that IP address space and press enter. And I wanted to show you that at least once so you don't feel bad. Because if it's the first time you've configured a Cisco router, there's going to be some things where it barks at you, and that's cool. It doesn't have an attitude, and it'll let you try again and again. So no worries. Next, let's go ahead and exit out of interface configuration mode. We're still in global config. Let's go over now to interface gig 2/0. We'll do that by typing in interface gig 2/0, and then from here we'll do IP address for this new interface of 10.20, and this subnet is subnet 8. And then we'll put in the last octet of .1 with the same mask. And press enter, and it's done. So we'll type end. You can also type exit a couple times, that'll get you out. But either way, we're out of configuration mode, and we've assigned those IP addresses. Let's go ahead and configure router 2. So we'll hit the tab for router 2. So here on router 2, what we'll do is we'll go into interface gig 2/0. That's the interface that faces R1. It's between R1 and R2. And we'll give it the IP address of 10.20.8.2. That's the 8 subnet with the 21-bit mask of 255.255.248.0. And you'll notice once we've done that, because there's a dynamic routing protocol running, specifically EIGRP from Cisco systems, the moment that R2 has an IP address, they're communicating back and forth, R1 and R2, willing to share with each other routing information. And that's really important because we're going to need full reachability and routing information if we want a packet to be able to cross all 3 subnets. So let's follow up with the interface on the right of R2. That's interface gig 1/0. We'll give it the IP address of 10.20.16. This is the 16 subnet, .2. And the 21-bit mask of 255.255.248.0, and then we'll type in end to get completely out of configuration mode. So next, let's test this by going over to PC1 on the far left
And let's do some connectivity testing. And on this virtual PC, in this lab environment, if we do a show IP and press enter, it's going to show us its current IP information. So it's got the IP address of 10.20.0.11 with a 21-bit mask. That third octet represents that this indeed is subnet 0. And it's also got a default gateway configured of 10.20.0.1, which is the IP address we configured a few moments ago on R1's gig 1/0 interface. So let's go ahead and do a ping of 10.20.16.22, which is PC2's address on the right-hand side of our network, and we'll press enter. And that looks great. That's a home run from end to end. And if there's any portion regarding the IP addressing or the subnetting that was foreign to you, or you want to revisit it again, I would invite you to take a look at the previous nuggets on IPv4 and subnetting in this module, which cover each and every one of those details that led us to this point of implementing IP addressing on a routed network. IP version 4 is 32 bits in length, and the challenge is there's just not enough IP addresses to go around indefinitely. So to help compensate for that, over 2 decades ago, a newer version called IP version 6 was introduced, which is 128 bits long, and as a result is so huge and has so many possible addresses, we're not likely to run out of any of those addresses in any of our lifetimes. And here's how it works. It's 128 bits in length, and it's represented in hexadecimal. Hexadecimal has the following characters. It starts at 0, goes all the way through F. So all the way from 0 to 9, it looks and feels a lot like decimal. And then once we get over 9, it goes to A, B, C, D, E, and F, and that's the full range. 0 through F is 16 unique characters. And each of these characters in an IPv6 address is representing 4 bits of data. And there's 8 groupings of those characters, and they're separated by colons. At the tail end, we have something that's familiar to us, and that is a slash and a number. In IPv4, that represents how many of the bits going from left to right are representing the network address. And in IPv6, it means the same exact thing. And when looking at an IPv6 address, we can identify that it's a globally routable unicast address by looking at that first grouping of numbers. If that first number is within the range of 2000 through 3FFF, ta-da! That's a globally routable IPv6 address. Now, a big difference, a huge difference between IPv4 and IPv6 is the fact that IPv6 does not use a broadcast. There's no all points bulletin that everybody has to listen to in IPv6. Instead, they rely on multicast and multicast groups for that. And if we're looking at IPv6 multicast addresses, anything that starts with FF, that is a dead giveaway. That is a multicast address. And one core protocol that's used by IPv6 is called NDP. That's the Neighbor Discovery Protocol. And NDP relies heavily on multicast traffic to communicate on local network segments. An example of using multicast is a router doing a router advertisement, or RA, that basically says, hey, I'm a router. And anybody looking for a router can tune into that frequency, can listen to that multicast group, and discover who the router is for that network segment. Or if a device needs to learn the layer 2 address of another device on that same network segment, in IP version 4, we would use ARP with a broadcast associated with that request. In IPv6, they would use Neighbor Discovery Protocol. And inside NDP, there's a suite of tools and functionalities that IPv6 can call on and use as part of the protocol stack. And similar to IPv4, we can also train our network by using static routes, or we can use dynamic routing protocols. For IPv6, we have RIP, NG for next generation, and we have OSPF version 3, which is also IPv6 specific. And these are examples of dynamic routing protocols that we can use with IPv6. We also have some shortcuts that we can use. We can leave off any leading zeros in a grouping. So instead of writing 2001 0 db8, we could put it down like 2001 colon and then db8, and any leading characters out of the 4 that should be that are missing, the system just assumes, oh, there's a leading 0 there, I get it. Another shortcut when representing IPv6 addresses is that if there's multiple groupings of zeros, like right here, we have 2 consecutive groups of zeros, we can represent that by just putting a double colon in. So if we finish this IP address, this would be 6783, and then to represent these 2 or more groups of zeros, we just use back-to-back colons, just like that. And then we'd finish off the IP address. So the 0090 could be represented as 90, the 0F0A could be F0A, and the 0B00 could simply be B00. Or, if it's close to Halloween, boo! and then followed by the mask, which indicates that the first half of this IPv6 address is the network, and the last half of this IPv6 address is the host address portion. Now, it's very probable that we're not going to be able to roll out IPv6 and have it be used exclusively because there's so much IPv4 in place. So if we had an area of our network, let's say over here, that's running IPv6, and up here in the branch office, we've got a portion of people there running IPv6. And let me go ahead and put in green right here between this router 2 and router 1 in the firewall. Let's say this is IPv4 only. How do we get connectivity across an IPv4 only network if we're using IPv6? And the answer is we're going to cheat a little bit with some tunneling. And tunneling is about taking a packet and wrapping it up into another packet so it can cross a portion of our network. So we could have IPv6 here. We could encapsulate that or put that into a new IPv4 packet as it crosses the network here, and then have another device on the other side de-encapsulate that or take out the original packet for IPv6 and deliver it to its final destination. It's also very likely that if we have multiple protocols running simultaneously in our network, that we're going to need some routers who understand both languages, both IPv4 and IPv6, so they can deal with both of them. And when a router or a device is running two different protocol stacks, like IPv4 and IPv6 at the same time, that's referred to as a dual stack system, or dual stack device, or dual stack router.
Thanks for watching our second, and press the button below, like, subscribe, and bell icon.